Modern data center powertrain units manage massive electrical throughput. Raw utility voltage courses through heavy copper busbars, creating high-density energy required to sustain critical server racks. At this scale, mechanical breakers move copper with immense force, but they lack the capacity to sense subtle environmental drifts. A breaker can trip on a short circuit, but it cannot see a drop in airflow or a localized temperature spike. Without constant supervision, these small deviations can propagate into hardware failures long before a primary protection relay reacts. Tracing the single-line drawing, we find the supervisory point for these systems, the Auxiliary Control and Monitoring Panel, or ACMP. It draws power from the main switchboard through dedicated breaker Q13, routing energy away from the critical load path into a separate monitoring architecture. The ACMP handles two primary tasks. First, it distributes that AC power to the module's vital support systems, acting as the local source for room cooling units, lighting, and exhaust dampers. Second, it provides the module's local logic. A portion of the incoming power is stepped down and converted to create a 24-volt DC control bus. Backed by dedicated internal batteries, this bus ensures the local processors and network switches stay online even during a temporary loss of the primary AC feed. Telemetry from the UPS, environmental sensors, and field devices streams backward to the panel. Here, the data is processed by the local controller and translated into an interface for the operator. Because the ACMP remains isolated from the critical IT load, it serves as an independent observer. Its operation guarantees the visibility necessary to keep the main power path online. Protecting this monitoring system from electrical faults requires strict geometric and electrical segregation inside the cabinet. The incoming 400-volt AC power is strictly divided. Zone 1 contains the auxiliary branches. These individual circuits run through miniature circuit breakers to feed mechanical systems like the room cooling interfaces and fire suppression panel. In Zone 2, a portion of that AC power is regulated to create the 24-volt DC bus. This low-voltage architecture powers the automation controller, the touchscreen interface, and the network switches. If an external exhaust fan short circuits, it will trip its specific AC branch breaker in Zone 1. Because the DC bus is isolated, the touchscreen remains energized. The system retains the ability to report the exact nature of the failure, preventing operators from mistaking a localized field trip for a total failure of the control system. All screen data traces to 4 channels. Discrete digital inputs report the status of smoke detectors or breaker contacts, while analog inputs provide a continuous stream of environmental measurements, like temperature and humidity. Relay commands execute digital outputs to move exhaust dampers, while detailed UPS telemetry arrives over the communication protocol network. This structural segregation ensures that monitoring logic persists even when high-draw mechanical components fail. Operators maintain the visibility required to diagnose the ecosystem from within a protected zone. Bringing the ACMP online requires a disciplined sequence. Before initiating startup, operators verify switching authority, confirm that panel covers are secure, and ensure no maintenance is in progress within the physical field boundary. Energization begins by closing the upstream feeder, Q13, at the main switchboard. This provides source voltage to the ACMP, followed by closing the local main breaker to initiate the internal bus. Operators then switch on Q6 for LED lighting, followed by Q10 and Q11 to energize the 24-volt DC control bus. This brings the controller and network switches online. Next, breakers Q4 and Q5 are closed to provide the high-voltage supply for the room cooling units. It is important to note that supplying power to these breakers does not automatically start the cooling units. The units have their own local controllers and breakers that must be verified as part of the thermal startup. Finally, operators close the remaining breakers for sensors and display equipment. This establishes the communication links required for the HMI to receive data from the field. As the HMI boots up, the operator reviews the overview screen to confirm 0 critical alarms, logging this as the baseline normal state. Following this sequential rhythm allows the operator to bring monitoring systems online in a controlled manner, establishing a stable stream of telemetry for the facility. The HMI overview screen is a rapid triage tool, designed to show the status of the UPS, cooling, and battery nodes at a glance. The color logic provides immediate situational awareness. Green confirms normal operation, amber signals a warning, and red indicates a critical abnormality demanding immediate intervention. For deeper electrical detail, the diagram screen translates the single-line drawing into live telemetry. Here, operators cross-reference 3 parameters for every breaker: open or close status, trip status, and rack-in alignment. Checking all 3 columns is vital. A breaker showing a green close status is not safely seated if the protection relay registers a red trip status. Misinterpreting these values can lead to unsafe switching decisions. Successful operation relies on the rule trend before alarm. While an alarm indicates a breach of limits, watching trend lines allows operators to catch system drift while conditions are still recoverable. Operators apply a standardized scanning rhythm. This begins with a 1-minute check of the overview page to identify new color indicators, followed by a 5-minute audit of the UPS telemetry page to verify that voltage and current remain balanced across all 3 phases. Every 15 minutes, the focus shifts to the thermal environment. Operators verify cooling run modes and chilled water flow. If ambient temperatures begin to climb while the cooling unit fan speeds remain static, it indicates a control failure that hasn't yet reached a hardware alarm threshold. On a shift-level basis, operators perform a deep audit of the battery system. This involves scanning individual rack and cell tables for localized temperature spikes or voltage imbalances that are not visible in the top-level state of charge metrics. Hydrogen gas concentration is the highest priority life safety metric on the environment page. Any elevation in H2 concentrations in the battery room requires immediate escalation according to site emergency procedures. Monitoring these trend mines provides the time necessary to correct thermal drift or gas accumulation before the automation system forces a critical shutdown. When investigating faults, operators apply symptom-to-root logic, tracing the physical path of power and data backward from the digital alarm to its exact origin. Consider an isolated failure. If a single analog sensor drops offline, the technician targets that specific input loop for field inspection. However, if multiple unrelated field devices vanish from the interface simultaneously, the system is experiencing a cascading failure. In a cascading failure, chasing individual sensors is inefficient. Instead, operators must immediately inspect the core components common to all devices, the 24-volt DC bus or the main Ethernet switch. Operators must also recognize the limitation of the HMI's acknowledge button. Pressing it only silences the active buzzer. It does nothing to correct the underlying physical defect. The fault remains until the operator traces the symptom backward, physically investigates the source, and corrects the hardware alarm in the field. Because accuracy is critical, network settings and time synchronization protocols in the setup menu must never be altered without formal authorization. Discrepancies in the local panel time destroy the chronological alignment of alarm records during a post-incident investigation. Tracing digital symptoms backward through the physical architecture ensures that localized mechanical trips are not misdiagnosed as a total loss of the monitoring system. If the ACMP itself requires maintenance, the shutdown demands a specific sequence. Before cutting power, operators verify the current cooling state and battery status to ensure the PTU is stable. This is a high-stakes action. Shutting down the ACMP removes required environmental monitoring from a critical system that remains live and energized. Before power is cut, operators must capture the current screen status and export the alarm history to preserve the forensic data for the period the panel will be offline. This procedure highlights the boundary of the digital interface. The touchscreen is highly accurate, but remains a monitoring aid, not a guarantee of physical safety. An on-screen reading of de-energized cannot be used to authorize physical contact with electrical components. While a dark screen proves the internal low-voltage DC bus is dead, it proves nothing about the state of the heavy AC terminals or the upstream feed. Electrical safety can only be proven by physical isolation. Operators must physically probe the heavy AC terminals with approved testers before breaking the boundary. Finally, operators must secure approved lockout-tagout equipment directly onto feeder Q13 at the main switchboard, mechanically preventing accidental re-energization during maintenance. By holding to a rigid data rhythm and proving safety through physical verification, operators ensure the ACMP reliably protects the continuity of the entire powertrain unit.